Great to be part of this community. It's amazing to see how many people are playing RISC-V. So I'm going to talk today about the vector extension. I talked about this before a little while ago. This is version 0.2, I guess. So just to recap on the goals of the vector extension, we want to make it efficient and scalable to all reasonable design points. So we actually want to build vector extensions for low-cost microcontrollers as well as the biggest, beefier supercomputer. We want to make it work well across all different microarchitecture styles, so in order, decoupled, out of order. And we want to make it support lots of different data types, so integer, fixed point, as well as floating point. It wants to be a good compiler target. That's very critical. And in thinking about compiler targets, the programming model is important. So we want to support both auto-vectorization as well as explicit SPIMD-style programming, like the OpenCL CUDA-style model. It has to work nice with virtualization layers. It's going to be part of Linux and needs to be able to use this stuff. And one of the goals of the standard V extension is it fits into the 32-bit fixed width encoding space. That's just to make it easier for people to use in other applications. But the goal is to actually have this be a base for future extensions on top of the vector facility. So for example, things like crypto algorithms we see building on top of this, and some other extensions will probably build on top of the vectors. So just a summary of where we are with this. So I made a presentation, I'm just looking back, it was actually June 2015, which seems like 3 or 4 years ago in RISC-V time, but only 12 months in real time. Progress has been pretty slow last year. Basically, there was a lot of other stuff happening. But now it's I think it's time to go back to this. I think I would say other things are more important than this, right? The last year, that's why we weren't focusing on this. But I think now is the time to go beat on this in detail. So forming a working group, I'll be the chair. And the goal is really to have this ratified 12 months from now. So next, the 7th workshop, end of next year. So there's a lot of work to do until we get to that point. So key features of the V extension, it's Cray-style vectors. For those of you who don't know about Cray-style vectors, go read about them. It's the right way to do SIMD parallelism. Forget about PackSIMD, forget about GPUs. Those are really dumb ways of doing it. Go read about Cray-style vectors. One of the features here, we support implementation-dependent vector length. So the same binary is going to run across implementations with different amounts of hardware resources. So it doesn't matter if you have one 32-bit lane or 58, 64-bit lanes. The same binary will run and run pretty well. It's a reconfigurable vector register file. I'll talk a bit more about that, and it supports mixed precision. So the state of the machine, you start with the standard scalar RISC-V state. You have the X registers, the F registers if you have floating point. And what we're adding is 32 vector data registers, V0 through V1, as well as 8 predicate registers, VP0 through VP8, VP7. And then there's a few CSRs that control the vector configuration. So I'll go through these pieces. One thing to note about the vector data registers, there's a variable number of them, depending on how many you need right now. And the width of each element varies depending on what you need right now. And I'll talk about that. So when you're running the vector unit, at some point in time, it has a configuration. And the configuration tells you for each architectural vector register, how many bits per element in that vector data register. So in this example, V0 and V1 are holding, say, a 16-bit float. V2 and V4 are holding 16-bit INSA floats, and V6 is holding a 64-bit value, for example. And then there's 3 vector predicate registers in this particular configuration, right? So the thing to notice is each element position in the vector has a set of registers, the data elements and the predicate bits associated with that element. Okay, so from the programmer's perspective, to use Guy Blalock's terminology, there's an array of virtual processors. Each one has this little local register set with different widths inside. Now, once you configure the vector unit, dependent on your physical implementation, you're going to get a different maximum vector length that depends on how many registers are using, how many bits each element is using. So the maximum vector length is a function of that configuration, the physical register storage in your machine, and also the microarchitecture. But luckily, software doesn't have to know much about this, as I'll show you as we go through. So when you're adding the vector extension to a RISC-V system, the types you must support in the vector extension depend on the base ISA and the extensions you support, as this table shows. So in an RV32i system, you have to support 8, 16-bit, and 32-bit fixed point types. And 64, you have to also do 64-bit, and RV128, you have to also support 128-bit integers. If you have the floating point extension, so one interesting thing, if you add vector floating point, you also must add half precision floating point to your system. And when you do this, you're also going to add half precision scalar operations too. So we have no intention of supporting, as a standard thing, scalar half precision float operations, but we want to support them in the vector unit. And if you have vector half precision, you need scalar half precision to keep the compiler writers sane, okay? So you have to add scalar half precision when you add floating point. And as you add the different floating point types, D and Q, you have to support those corresponding element widths as well, okay? So combination of the base plus the floating point, the base ISA plus the floating point extensions define the mandatory types you have to support in the vector unit. So how is this configuration represented? So I'll go over this. This is something that's changed a lot over the last year in working through some of the software issues. So each vector data register has a 4-bit field that encodes the maximum width of elements in that vector. So this is just the raw bits in that vector element. So it can be 8, 16, 32, 64, 128, or disabled, which means I don't need this architectural vector register right now. And so there's a total of 128 bits of width configuration that are held in a single CSR on RV128, 2 in RV64, or 4 in RV32, like just the way we handle the 64-bit counters in RV32, right? So RV128, a single register holds all 128 bits vector data register configuration of the width. Okay, so that's the width. Separately, there's a type encoding, and that's shown in the middle column here. So each vector data register has a type encoded in a separate piece of configuration state. And it separates whether it's floating point or integer and how many bits of precision or if it's disabled. Now, in many use cases, you're only going to set the maximum width and the type at the same time when you enter a loop nest. And so in the architecture, if you write to the maximum width field a value corresponding to the type, you will write both those. Each vector data register has a maximum width and also has a type field, which is a separate 4-bit encoding. I'll get later on, I'll explain why we split the width and the type this way. But basically, most use cases, you're going to write the max field. When you write the max field with the value from the type encoding, you write both of the fields. And the width information is preserved in max_w, while the type thing holds the entire type, right? So you might notice here that max just cares whether it's 16 bits. It doesn't care whether it's 16-bit integer or 16-bit float. Type will record that. Now, at any time, you can change the type independently of the width, provided it's less than or equal to the width. And when you change just the type field of a register, it just zeroes that one vector register. What I forgot to mention is if you change any part of the maximum configuration, the entire vector unit state is initialized. And in fact, anytime you change any of the configuration that corresponds to the maximum vector length, the entire vector state gets initialized. But if you change just the type of a single register, just that single register is zeroed. So the vector predicate configuration is much easier. You just have a single register that says how many predicate registers you're using. Okay, and any write to this initializes the entire vector unit state as well, because changes in this will change the maximum vector length the hardware can support in general. Okay, now there's a bunch of bits there in the configuration. And so if that was the only way to set the configuration, it would kind of be slow in a lot of use cases to configure the vector unit for a loop nest. And so to make it faster, we added an alias, which is a way of writing all that information in a compressed form for some common usage patterns. And so this vector config D alias has this format of fields in there. So for example, this says how many 8-bit fixed point do I need, how many 16-bit fixed point, 32-bit fixed point, and so on. How many vector registers of this type do I need? And the way it's encoded is you write in there the highest vector register number of that type. And so it's easiest to see with an example. So this is this thing laid out again. So for example, say I wanted two 32-bit integer registers, 12 32-bit floats, and 18 64-bit floats. I would do, oh, it's actually 18, right? This says vector register 1 is the highest one here, vector register 12 is the highest one here, vector register 18 is the highest one here. So that means V0 through V1 are type x32, V2 through V12 are F32, and V13 through V18 RF64. So this is just shorthand way of setting the configuration. It doesn't add any more state. It's just a way of setting the existing state that sets the configuration. Lets you do it more quickly. Okay. And notice that you're writing both the type and the max at the same time with this information when you do this. Okay. So this all seems a little complicated. I'll get to an example soon, hopefully explain why we're doing these things. So one thing about this, the Vmax and the V number of predicate registers, they set, for a given hardware implementation, they'll set what's the maximum possible vector length you can support. We call this MVL, right, maximum vector length. Notice that changing the type of a vector register doesn't change MVL, and that's important. We'll get to why. So any change to the configuration that changes the maximum vector length will clear all the vector unit state. And there's a bunch of reasons why we do that, require that, is you don't want to have the program rely on state in between reconfigurations. We want to give flexibility to the implementations, how they map bits between different configurations. And we want to avoid any security holes from leaking state in sort of unused bits of the vector unit. All those instructions that change the configuration, they're encoded as CSR read-write instructions, and they're encoded as swap instructions. So what you write is the new configuration. What you read back is actually the MVL of that configuration you just wrote, right? This is a little bit different than a plain CSRW, which gives you the old value you read. You write the configuration, what it returns is the MVL of that configuration, right? And if you update the configuration in steps, each step will return the current MVL for what the current state is in the vector unit. Now, one thing to note is this MVL, programmers often get hung up on this. Most code will not use MVL directly at all. And the reason is we have this set vector length instruction, which is usually the way you get at work with the vector unit. So the active vector length is held in a CSR called VL. And this, at any point in time, can only hold values between 0 and maximum vector length inclusive. So any configuration changes will initialize this to the maximum vector length. So usually the way you use this is you modify it with a set VL instruction, which is also encoded as a CSR read-write. And the source argument is the application vector length you'd like to use. And what it returns is the actual vector length you get to do that time around. And there's a little heuristic on how you set this, which is if the requested application vector length is less than the maximum vector length, you just use that application vector length. If it's greater than twice the maximum vector length, you use the maximum vector length. If it's between 1 MVL and 2 MVL, you halve it, and that's the value you use. This is a neat trick, which basically balances the load across 2 strip-mine loop iterations. So if you want to think about a case where you have a vector length of MVL of 64 and an application vector length of 65, it's kind of bad if you do one strip-mine loop of 64 and then do another one of length 1. Generally, you get better performance doing 30, 32, and 33, right? So that's kind of what you'll get by this heuristic. So it just balances the last couple ones. You don't get this weird last iteration with almost no elements that works really low efficiency. This is an idea the Cray guys used a long time ago. Okay, what does vector-vector add look like? So let's do a 32-bit integer vector-vector add. So I've got 2 vectors in memory, add them together pairwise, and storing the result back to memory. So first thing I need to do is configure the vector unit. So I say I need 2 32-bit registers. With a fast configuration instruction, that'll only be a couple of instructions, one to load an immediate, one to do the write to the configuration register. I then set the vector length here. A0 holds the application vector length. You can imagine as a function with arguments A0 through A3. Set the vector length. So T0 will then tell you how many elements are going to be done on this iteration of the strip-mine loop. So I load the first vector into V0, I load the second vector into V1 from these pointers. I add them together into V1, and then store V1 back to memory. Then need to do some scalar bookkeeping. I multiply the amount I did by 4 by doing a shift to get the byte count. I then update all the pointers, subtract how many I did this time around, and jump back around to finish off. Okay, just iterate around until it's done all the elements in the vector. And then when you're done, you actually, there's another instruction that will just clear all the configuration state and turn off the vector unit, right? So outside of the vector loop nests, the OS, for example, doesn't have to save and restore the vector context, right? It's not there. Something to note about this. So it doesn't matter what the hardware maximum vector length is. The software loop doesn't care about that, right? It's sort of hidden from it. This same binary will run on machines with 32-bit vector registers or 16 kilobit vector registers, right? The same code will run. Okay, it's hidden in the software through that setvl instruction, right? So it also doesn't care how parallel you do this. Do you do it 32 bits at a time? Do you do it 1024 bits at a time? The code doesn't care about that. So this is 32-bit integer vector add. Let's try and do, interesting, let's change it to 16-bit vector integer add. How does that work? Well, I want to say, I want to do some 16-bit, but I need two 16-bit vectors now. Code is almost identical, except I'm going to multiply by 2 to get the bytes. I bump the pointers by instead of by 4. Okay, so that's vector add of 16-bit integers. So that's pretty cool. What's even cooler, let's add 16-bit vector to a 32-bit vector. Okay, so I now have to say, well, I want one of each. I load the 16-bit vector, I load a 32-bit vector, I add them, I store the results, bump the pointers. Some are bumped by 2, some bumped by 4x. Subtract how many done, strip mine, and go back. So any of you who've programmed a PAC SIMD machine will understand that this is way, way, way simpler than doing this on any PAC SIMD machine. Okay, right? And notice that we don't care about the alignments of the vectors. We don't care about the length of the vectors, whether they're a multiple of the vector, the PAC SIMD width. We don't care about the hardware implementation. How does it manage mixed precision, 16-bit, 32-bit? That's all hidden from the assembly code. So different implementations can implement the vector unit very different ways and still run the same code. For this example, at pretty good efficiency. Okay. So this is just kind of summarizing some of those things. You get the same binary code regardless of number of physical register bits, number of physical lanes, mixed precision packing strategy. Okay, it doesn't matter. Same code is going to work. Now, one detail in here, there are certain cases where you don't want to even have that strip mining loop overhead. And so the architecture is going to guarantee that you have a vector length of at least 4, regardless of your configuration, right? So it doesn't matter what the configuration settings are. Your implementation must ensure you'll always get vectors of length at least 4 coming out. And the constraint in this place is on the minimum implementation isn't that great. It just says if you have, say, a 32-bit microcontroller that wants to add vector extensions, integer fixed point ones, it needs to have 1 kilobyte of SRAM to store the vector state. That's kind of works out to. So this is a constraint, but it doesn't really it's not a tough constraint for even small implementations to meet. Okay, so one detail here is sort of hidden in there is to kind of help pack it in the opcode space and manage these different types. We use a polymorphic instruction encoding. So basically, an add opcode looks at the types of the operands which are held in those configuration registers to figure out what to do. So assigned integer add always does assigned integer add. The operands may be 16-bit, 32-bit, or 32-bit and 16-bit added together, as an example. So in the spec, we're going to list the combinations that implementation should support and as the base standard. And those will mostly be things like going up by 1 power 2. So for example, 8 plus 16 adds should be supported. 8 by 8 multiplies into a 16-bit result should be supported, and so on. So there'll be a sort of a matrix of which operations you need to support for each of the opcodes in the spec. So vector loads and stores, very important. So unit stride, constant stride, indexed for scatter gather. The types are inherent in the destinations. You don't have to encode that in the types, which saves a lot of opcode space. I'm also going to support vector AMOs, so vector fetch and add, for example. So vector predication, this is how we do conditional execution in the vector unit. There's up to 8 vector predicate registers, 1 bit per element. We support logical operations between these. So in the base, I say the idea is it's really hard to fit this into encoding space. So everything is encoded under P0, predicate under P0. But we have instructions to swap predicate registers. So in complex, you can just use that or fuse that to get the effect of having a wider word with the predicate registers. The idea is maybe later we'll do a 48-bit encoding that gives you more direct access to a larger space here, but to fit it into 32 bits, this is the thing we did. There's pop count to get you the bit set in a predicate register, so you can do scalar control. And there's other flag I don't have time to go into some of the other flag operations that we're thinking of adding to support some complex loop optimizations, and also adding support for software vector length speculation. So if you want to vectorize a while loop, you need some way of doing operations that you're not sure you should have done. And so that's handled through the flag mechanism as well. So talking about predication for a bit. So there is this complication with vector predication and vector register renaming. if you want to combine a out-of-order core and a vector unit, there's many paths of doing that. One way is to actually implement full vector register renaming. And the predication scheme, there's a few things you could try. One is the obvious one, which is the classic one. The destination has the old value if the predicate is false. That's a simpler spec, but it's better for in-order machines if you don't have renaming. But it makes a rename machine have to copy the old value into the destination if it isn't changed. Or you could have a scheme where if the predicate's false, you write 0 to the destination. That's better for renaming, worse for in-order machines, because now you need extra code to undo that or work around it. Or you could, like the Cray guys, made it undefined if the predicate was false, which is, I think, the worst thing to do. Just in terms of everything gets more complex and you have a messy definition of what that means. So I think our current plan is to go with 1 and rely on microarchitectural tricks for the out-of-order vector registers we're renaming. Got some ideas on how to improve that. OK, so I talked about how the configuration has a maximum width and a current type. Now, why did we do that? The answer is vector function calls. So when you write vector code, you want to vectorize a classic loop, like in auto-vectorized code, say I have a loop like this that calls an exponential function. I could inline exponential everywhere I use it in vector code, but it's going to get pretty big pretty soon. Blow out my iCache maybe. So what you want to have is internal to the vector runtime, you usually have a vector calling convention that calls into vector millicode libraries to implement these transcendentals and other kinds of function. So you want to actually call a vector function with arguments in vector registers and with vector length and masks, giving you which active elements are there in that vector function call. And the difficulty here is when you have a reconfigurable vector register file, I want to abstract away, I need to hide how the callee is going to use registers from how the caller is using registers. So you have to agree on some mechanism to share values in registers. Now you could just go through memory, but if you do that, you kind of, on these lot of loops, you can lose a lot of performance. You want to be able to pass arguments in registers to these vector functions. So the idea here is the caller has to allocate registers for the callee to use, and it's going to do them by setting the maximum width, and then the callee can then change the type according to whatever the callee needs to do inside that vector function call. Now, there's a lot, so in the hardware mechanism is there. It's then a question of how the software protocols are going to use that hardware mechanism. So in the case of an auto-vectorized system, the runtime here is probably it can optimize its whole call tree for all the vector functions in the vector runtime library to optimize its calling conventions. You could do that. You could instead come up with a standard one where there's some policy. You just look at the code and come up with how many registers does the code have to leave available for any vector function call sites, right? So one thing is if you have a loop nest that doesn't make any vector function calls, you can just allocate the vector register space as you see fit for that one loop nest. But when you have to do vector function calls, you have to worry about this calling convention, right? So in the case of auto-vectorization, there's some possibility you could optimize it for the current set of runtime functions you want to support. What's a little more complicated is when you have a SPMD programming model like OpenCL or CUDA, and here like everything is vector function calls, right? All the code base is written that way. And so you have to configure the register set once when you launch kernels onto the device, right? And they can call arbitrary amounts of code. So here you pretty much have to, you maybe end up setting everything to be maximum width and just use some very conventional equivalent of the scalar calling convention in the vector side, right? You're going to lose a lot of the vector length flexibility here. But like the first bullet says, this is really not a good programming model. I mean, it's really a pretty lousy way of programming a vector machine. It is a standard one. There's a lot of code out there, so we need to support it. But really, if you would prefer to have the auto-vectorization, most sane people would much prefer that over writing OpenCL and CUDA code if we had the right auto-vectorizing, auto-parallelizing compilers, right? It's much, basically writing a few pragmas around a loop is much easier than doing OpenCL or CUDA. So that's kind of what we should do, but we can't handle this. And one other thing is the divergent control flow. If you want to know how to do that with predication, you should read Jan Substhesis. It's all about how to do that efficiently just using predicates. Okay. So briefly, OS support. So what we'd like to do is support simpler implementations that may want to support only restartable page faults. And the model here is similar to the DEC VectorVax, where there's basically an opaque blob, which is the vector unit state. So when you get a page fault trap on vector accesses, the OS just has to reserve enough memory to dump a blob It then services the page fault, reloads the blob, and restarts the vector process. But if you have an implementation that's precise traps, you can just skip that by effectively the 0 state to store. So the OS doesn't have to worry about it in that case, right? So we want to support both implementation styles at the OS level. In the privilege spec already, we described this XS field, which can be used to indicate if there's any state at all active in the vector unit. So when you're not using it, there won't be any OS context switch overhead to saving or restoring it, right? You just unconfigure it off by default. Okay, that's it. Simple, right? Any questions?
Two quick questions.
Yeah.
Jan Gray, Gray Research. Have you thought about even narrower vector element types like 4.2 and 1 bits? And the second question, what's the extensibility model for vendors that want to add additional operations to the vector operations you've got? Like, let's say you didn't have max and you wanted to add max. How does that look?
Yeah, okay. Start with the first question. Yes. So you notice the type encoding is not fully utilized. So as well as 1.2.4, I've been thinking about 6, 12, and 24, and 48. Okay. And sounds a bit crazy, but I think actually with the, if you look at how we built Hwacha, which will be open source now or soon, that's an example of an implementation that supports mixed precision. I think we can actually support non-Para 2 types reasonably cleanly as well, in a lot of cases. And I think there's some space in that 4-bit field. You could add a second CSR that had an extended type to support other types. Yeah. Second question was
adding new operations.
Adding new opcodes.
Like
sure. So I think the goal is to have the base set fit in the standard 32-bit fixed width encoding. There should still be plenty of space to add additional opcodes. And we should figure out where so one thing, like I mentioned, we want to add support for things like crypto and other operations on top of this. So we need to figure out how to manage opcode space for all those other things you want to do with, big chunks of bits.
Thank you.
Yeah.
So I had a question about predicate registers. So do you predicate on the input operands or on the output? I'll give an example. Suppose you're doing an add versus a dot product. V1 and V2 are 2 vectors. So do you predicate on, say, the fields of V1 and V2? Or do you predicate on the fields of the destination, saying that if predicate falls, don't write to destination? So
it's the latter.
The latter. So you don't take care of, let's say I want to zero out fields in a vector. So I'll have to do that before I commit it to multiplication.
I guess so, yeah.
Thanks.
Peter Shu Consulted. So, excuse me. So when people build these vector things with predicates and out of order and AMOs, there's this complicated thing that happens with the AMO and predicated stuff. So are you guys stacking that up?
Yep, we built a lot of vector machines with predication and AMOs already. The complication of predicate is actually with any memory operations, particularly stores, not just AMOs. And yes, it's a complication, but yes, you have to do it to make code work. I mean, it's not terrible. We've done it many times. Many people have done it. But you have to be aware of, in building microarchitecture, for example, a predication on a store operation, you have to know the predicates before you update anything in memory. And that can break decoupling in a pipeline, for example. So that's the biggest impact really is on the predicate decouple. The otherwise decoupled unit ends up becoming coupled through the flag set operations. Yeah.
Okay.
Yeah, we built many vector machines.
So there's something similar with like scatter gather and predicated on vector machines and this page fault thing. Right, because when you predicate it, there are these page faults that then become not really happening. And
yep. So one thing we do is we, in our implementations, what we've done a lot of is use a vector refill unit that actually runs ahead of the vector unit. And what this does is actually prefetches into the cache, which is a safe thing to do. It cuts down the amount of low data queue buffering you need in the vector unit, and makes it easier to hide some of those latencies. Basically, using prefetch, including prefetch with intent to modify. You don't actually have to modify, but it cuts down the problem case of if you really had to wait to be really sure before you did every one. It could be really slow. By doing the run ahead, which is really easy to do non-speculatively because you know exactly what vector instruction you're going to do, you can sort of bring it up through the hierarchy before you get to finally commit to doing a store. So yeah, there's a paper, I think Micro 2004, we did a paper on how you do that. And it really helps cut the dependency of memory latency on how the performance of those predicated memory stores. Yeah, okay. Hey, Lisa.
Lisa Wu, UC Berkeley. So I have a question about your vector add example. So you have this 16-bit integer add to 32-bit integer, and then you're doing this implicit, I guess, zero extend on the 16-bit integer.
This
What
would be
about-
sign extend in this case, yeah.
So
The
what
add-
about
yeah.
floating point 16-bit add to 32-bit? Are you implicitly specifying up convert, down convert?
Yeah, so the model will be if you have two different sizes in a floating point operation, you would promote the lower one up to the higher one, which is, preserves everything, and then do the add as if they were the same size. So it worked that way. That's, yeah.
And then another question is about floating point exceptions. So are there any registers you're specifying to store those data? Are you planning on supporting floating point exceptions?
Yeah, so the floating point exceptions will be stored in the regular floating point CSR. So it all accumulated into one place. One place where you have to be a little careful is doing the speculative vector length execution, where you don't want to fold in those exceptions till later. And so you want to actually put them somewhere else before you fold them in. But yeah, generally they'll be available just in the regular flags in the floating point CSR.
Stefano Rear, question, how do you handle vector reductions in this model? And all of the code examples I've seen for the V extension and Hwacha are for map type operations rather than reductions that produce a scalar.
Yeah, so the class that we do is a vector machine. You write a vector extract, or some people call it vector shift. So you can take the top half of one vector and put it at the beginning of another vector, and then you can just recursive halving to do the reduction. And that handles, pretty much all reduction types. Yeah, there's a bunch of vector permute operations I didn't go into that we're also thinking of adding, but that's the most needed one, is this vector extract, which pulls out the top half of one vector and puts it in the bottom of another vector.
Second question, are there complications in the calling convention because you don't know how large the registers that you need to spill are?
So the scalar calling convention is not affected. The whole vector unit state is considered caller save. So the callee is going to stomp on, it just assumes it can stomp on the vector unit for the scalar calling convention. So the regular ABI isn't changed. The vector calling convention is just used internally within the runtime or in an OpenCL runtime. And in there, like I mentioned, that's the reason we split the max from the type, so that you can save and restore because you don't need to do anything. You just save, do a load. A store is going to store according to the type it is. If you return the configuration and do a load, you're going to get the value back that was there originally. Yeah. So it doesn't affect the scalar calling convention at all. This stuff is all caller save, so it just gets wiped out. You assume it's wiped out across a function call. And for the vector runtime, like I said, there's going to be some more research to figure out what exactly is the best vector calling convention for vector millicode kind of routines. Yeah.
One last question. A lot of current SIMD code for cryptography and multimedia applications makes very heavy use of permute operations. Does that fit into this model at all?
Yeah, like I said, I didn't talk about permutes, but register to register permutes are one thing we're looking at. It is a little complicated to provide arbitrary permutes across arbitrary length, like implementation-defined vector lengths. But there's things you could do. There's certain patterns that work that you can build other permutations out from. Yeah.
Nikita Voronov from Esperanto Technologies. And can you state how do you convert between the vector lengths? For example, I want to do a 16-bit math, or in this example, and how do I do it?
I didn't understand. Can you repeat the question? I didn't understand.
Well, I load one 16-bit vector and a 32-bit vector, but I want to do a 16-bit math on them.
A 16-bit mul?
Math. A 16-bit add, for example.
You want to add 16 bits to 16 bits and return 16 bits?
Yes.
Then you would have created a 16-bit destination.
But no, I want to convert 32-bit to 16-bit.
Oh, you want to convert, sorry.
Yes.
Yeah, well, you have a convert instruction that goes from a 32-bit to a 16-bit register. There's a convert instruction
yes.
that goes from the source type to the destination type.
Okay, thank you.
Do you have some kind of quantitative metric why Cray style vectors are better than what is currently used in the industry, like AVX and so on?
I think about 40 or 50 years of experience.
But that's, it's you can say that like AVX is widely supported by the compilers as well.
Doesn't mean it's not. It's very, if you look at all the extensions they're having to add to improve what the compiler can do, like they don't have scatter yet. It's coming, but they don't have it yet. They just added load. In fact, gather very slowly recently. It's just not a good model. Like in this example, go code this in AVX.
Yeah, I know, but
so
what I'm trying to understand
what was the question?
Is that your claim is that it's,
Yeah.
let's say, 10% better performance?
No,
or is
the
that
machines we build seem to be substantially, like integer factors more efficient than GPUs and things on doing this kind of code. So, our experience of building this stuff is it's very efficient and it's very easy to program. So it's like hard to justify doing, just because people are familiar with this, or people who've only seen the recent machines are familiar with PackSIMD and GPUs. This older style is very, very effective. We built lots of machines and they tend to have leading efficiency numbers in terms of gigaflops per watt.
Is it like a factor of 2? Is it 10%? Or I mean,
I don't know. The last one we did was like 50 gigaflops per double precision watt. 50 double precision gigaflops per watt. So like integer factors. It's hard to normalize for everything. I'd say, yeah, more than 2.
Okay.
Hi, Paul Kotcher, Cryptography Research, Rambus. How much thought have you given to the question of how you verify that your hardware implementation is correct and also that software will work correctly across all possible hardware implementations?
That's a good question. So the first one is, is this hardware verification problem. That's a problem, and you just, with a given instance, you have to verify it works correctly. The second one is tougher. So how do you verify that a piece of software works across all implementations? Well, one step is if you have a spec of the vector unit, a formal spec of what the vector unit instructions are supposed to do, and then you'd have to verify the software works across all those cases, right?
So will there be a finite number of legal implementations, or is there basically an unbounded number of configurations of vector sizes and stuff like that?
Well, I think if you approach it that way, I think you'd have to say, like, for example, this thing works for any length vector. You can prove this works for any length vector. You can use it as a primitive in building a proof, right? You don't have to look at all combinations all the time, right? You can divide and conquer. Like, I know that this is going to do a vector operation of any given length n correctly, regardless of my implementation, right? Yeah.
Maybe.
Yeah. Okay. It's a good problem to think about.
Hi, Guy Lemieux from VectorBlocks. When you said reset the vector unit state, do you also mean the vector register file is zeroed out?
Yes. All the vector data registers go to 0,
Okay.
and all the predicates are set, and the vector length is set to max VL.
On an FPGA, that's going to be an incredibly expensive operation because it's got to be VRAM based. So I'm not.
No,
sure
you just use rename bits. You have a bit that says whether it's 0 or not when you read it out. You don't actually, you just check that bit and then return
that
0.
introduces a mux into the data path, which slows things up from a critical path perspective.
Yep.
So I'm just wondering, is there a reason that you have to do that?
Yes, I think the reasons are basically we don't want an initialized state to just show up in a configuration. We want to hide the difference between implementations. Getting back to the verification question, I doubt you could verify code running on any implementation. There's some implementations because have random bits appearing depending on the configuration you just did.
Okay.
So security holes, programmer avoiding weird cases in certain machines, or programmers relying on that state.
Okay, last question.
Sorry if this was discussed a little bit already, but so if this model, which was available for quite some time, is better, why did industry go the other way?
I could ask that question for X, where X is many things. I think. Sorry. Well, if you look at so MMX style actually predates vectors. It goes back to the TX2. If you go read, how that did partitioned its 36-bit data path into 2 18s and 4 9 bits. That's kind of obvious, easy thing to do. It's a cheap thing to do. It doesn't scale. But if you look what Intel has done, they started MMX because they didn't want to play with the OS. They just want to overlay it on the floating point registers, so the OS didn't have to save and store more stuff. Then they went to 64-bit. They needed more, 128-bit SSE2, SSE3, SSE4. Oh, let's do AVX. And it's a whole different set. One of the reasons the opcodes have grown so big is they didn't have a scalable plan. So every generation, you have to rewrite all your code to make use of the new width, right? Just a really dumb idea. It's obviously dumb. I don't know why they do it. I've talked to them at length about this. They keep doing it. I don't understand either. So part of the reason we did RISC-V and called it RISC-V is we want to do vectors. So,
Thank you.
so this is all a big ploy just to get vectors into the main line.
Why don't we end on that note?